All right, today we are diving into Lumo 1, which feels like a major step toward building genuinely intelligent robot agents. You know, the kind that can actually work in our homes and offices.
It's a huge paper. And what they're introducing is a new end-to-end model, a vision language action model, or VLA. But it's a VLA with a really critical twist.
And that twist is the structured reasoning. It's a chain of thought process that runs right alongside the action prediction.
Exactly. Which means for really the first time, we get this transparency into why our robot is doing what it's doing. It's not just an opaque black box anymore.
And they pull this off with a pretty big technical innovation, this spatial action tokenizer.
A total game changer for modeling motion.
Yeah.
It just so efficiently represents these really complex motion sequences in the end effector space.
Yeah, it gets around all those, clunky, inefficient binning methods we've seen before.
And the results really speak for themselves. Lumo 1 just consistently outperforms the state-of-the-art baselines.
Especially in the hard stuff. We're talking generalizable tasks, long horizon planning, and dexterous manipulation.
Right. It works with novel objects. It understands unseen instructions that require abstract concepts. It really feels like this model understands intent.
So let's unpack the big problem they're solving here, what's often called the robotics generalization gap. The dream for years has been an agent that can see, reason, and just coexist with us, handling instructions like, I'm thirsty, can you grab me something low-cal from the kitchen table?
And that's exactly where current VLAs fall down. I mean, even the huge ones built on models like Qwen 2.5 VL7B, they just struggle.
They have all this knowledge, but when it comes to taking physical action in the real world,
They break. They're not robust. They don't generalize. And you have no idea why an action failed because there's no interpretability.
yeah, because the current systems are just a direct mapping, right? Observation goes in, a control signal comes out, it's all reactive.
It's a reactive loop, not a reflective one. It's not how people work. We perceive, and then we evaluate context and intention before we act.
And that's the paradigm shift with Lumo 1. They're saying actions have to emerge from structured reasoning.
It's not just a function of what the robot sees. Technically, they do this by jointly optimizing over two things. The reasoning trace, which is just a text explanation of the plan.
The mu variable in the paper.
Right, mu, and the action chunk, which is the actual physical movement. By linking those two, the policy is forced to be grounded in the plan it generated.
Which brings us right to the technical core. How can you even model physical action efficiently enough to have any compute left over for all that reasoning?
Yeah, that's the key problem.
Because the old binning methods are just computationally brutal. 256 bins per dimension, over 6 dimensions, over 20 time steps. You're generating hundreds of tokens for one tiny movement.
The training complexity just explodes. It's unusable. So their solution is this spatial action tokenizer.
Okay, so how does it work?
They start by defining the action space in delta and effector space. So they're modeling the change in position, the XYZ, and the change in rotation, the SO3.
Wait, hold on. Why is modeling the change, the delta, so important for a generalist robot?
Two big reasons. It's compact, and more importantly, it's cross-embodiment friendly.
Meaning it can transfer between different robot bodies.
Exactly. Think about opening a cabinet. A little tabletop arm and a big mobile manipulator will have completely different joint angles, different absolute coordinates.
But the motion of the hand itself.
The relative motion is basically the same. Move forward 5 centimeters, rotate 10 degrees. This makes the learned skills, these motion primitives, independent of the robot's specific kinematics. It's huge for transfer learning.
Okay, that makes sense for the spatial representation. But a trajectory is still a sequence of thousands of tiny movements. How do they compress the sequence?
That's the next clever part. They use something called the AWE algorithm, approximating waypoints with error.
AWE. And it just decomposes these long, messy trajectories from, say, human teleoperation
into a minimal set of waypoints. It abstracts away all the noise.
And what kind of noise are we talking about here?
All the irrelevant stuff. The little hand jitters, micro movements, even differences in how fast the human operator was moving.
So if one person teleoped the robot quickly and another did it slowly,
the raw data looks totally different, but the functional path, the core movement, is identical. AWE just pulls out those critical waypoints that define the path. It simplifies everything.
So now you have these clean, essential waypoints. How do you turn the movements between those waypoints into tokens for the VLM?
They use key-means clustering. Simple as that. They cluster all those delta actions between waypoints.
And each cluster center becomes a motion primitive.
Exactly. That becomes their motion token library.
Right.
So a complex reaching motion might be represented by just a few tokens from this library instead of hundreds of raw numbers. They mentioned having about 150 clusters just for the left arm.
That is some serious compression. But, with compression comes the risk of error. What happens if the VLM predicts the wrong token? How do they stop the robot from just failing catastrophically?
The robustness is really baked into the design. First, they use a fixed action horizon, 40 frames, which is about 1.3 seconds. So it's only ever predicting the very near future.
Manageable chunks.
Right. Second, they synchronize the waypoint selection for both translation and rotation, which keeps the movements physically consistent. And third, during training, they use a top 3 token sampling strategy.
Which makes the model more resilient to small prediction errors.
And here's the most crucial part. Because every single token in their library is a known, valid motion primitive, the system is just inherently more stable. A small error might pick a suboptimal path, but it can't produce a physically impossible action.
That's a huge point for safety in the real world. Now, about that VLM backbone, it deals in these discrete tokens, but robots need continuous, precise movements. How do they bridge that divide?
Yeah, that's a classic problem. Training VLMs directly on continuous outputs is, well, it's notoriously unstable.
So they sidestep it.
Completely. They use a 2-step process. First, they train the VLM backbone purely on those discretized action tokens we just talked about.
Yeah.
Simple imitation learning.
Okay.
Then, during fine-tuning, they bring in a pre-trained flow-matching action expert. This expert handles the continuous part, giving them the precision they need without messing up the VLM's policy training.
So let's talk about that training. The scale here is just immense.
Oh, it's massive. The foundation is Qwen 2.5 VL7B, and they train it across 3 stages on something like 407 billion tokens.
Stage 1 was all about building that foundation for embodied reasoning, right? Just strengthening the VLM's multimodal understanding.
Yep. All the big data sets for visual question answering, spatial reasoning, OCR. They checked its performance on benchmarks like Spatial Bench to make sure it was ready to understand complex instructions before moving on.
And stage 2 is where the action comes in. This is where they co-train it on this incredibly diverse cross-embodiment robot data.
This is so important for getting that general physical intuition. They use data from 4 different robot platforms, covering 145 different complex manipulation tasks.
I thought their data handling here was really smart, especially how they dealt with operator bias.
The handedness problem. Yeah.
Most teleoperation data comes from right-handed people, which creates this big asymmetry in the data set.
So they just mirrored it. They called it robot trajectory mirroring. They'd flip the visual data horizontally.
And then negate the Y component of the end effector's position.
Right, because Y is typically the left-right axis.
Yeah.
Negating it perfectly mirrors the motion across the center. It's a really simple way to double your data diversity and get a balanced data set for both arms.
And then comes stage 3, the grand finale.
This is the core integration. It's focused just on the target hardware, the Astribot S1, and this is where they introduce that special structured reasoning action data.
This is where the robot learns to think. They have different reasoning types, like abstract concept reasoning.
The example they give is high-calorie caffeinated drink. The robot has to figure out that means the cola can.
Then there's subtask reasoning for breaking down big goals and just basic visual observation and movement reasoning.
And this final stage also gives us the 2 deployment modes, full reasoning and partial reasoning.
Full reasoning is the whole 9 yards. It parses the instruction, makes a plan, refines the plan based on what it sees, and then outputs the action.
Whereas partial reasoning just does the subtask part. It's the classic speed versus robustness trade-off.
Which brings us to the results. How did it actually do in the real world?
In the pick-and-place tasks, Lumo 1, the stage 3 version, just blew past the baselines, especially when there was any kind of novelty.
And this is where that reasoning really pays off, right? The unseen instructions category.
Absolutely. This is where it shines. The model could handle tasks that required real common sense, like manipulate the animal that eats bamboo.
So it has to first use its VLM knowledge to know that a panda is the target, then find the panda object, and then its policy has to actually pick it up.
Or find the sour fruit when there are apples and bananas on the table. It's a conceptual leap before any action. Lumo 1 nailed these tasks.
What about that reasoning mode trade-off? The paper says full reasoning was better for comprehension, but they recommend partial reasoning for practical use.
Yeah, it's all about latency. Full reasoning prevented some subtle planning mistakes on really complex instructions, but it's slower.
And for most day-to-day tasks, that speed from partial reasoning is just more important in a real-time environment.
Exactly. And after all that, they didn't stop. They added a reinforcement learning fine-tuning phase.
Using an objective called GRPO.
Right, GRPO. It's designed to boost performance without the model catastrophically forgetting all the knowledge it gained during that massive pre-training.
Why did they need such a complex reward structure for the RL? Couldn't they just reward success?
They needed precision, not just completion. So the rewards were super specific. They had visual rewards like IOU on bounding boxes, but the really interesting one was a DTW-based distance reward for the waypoints.
DTW, dynamic time warping.
Right. It's a way to measure the similarity between two sequences, even if they're out of sync. Using DTW as a reward ensures the robot's trajectory doesn't just get to the goal, it follows the optimal path to get there.
And you can see the impact of that in the numbers. The net superiority rate, the NSR, shot up after RL.
Huge gains. A 22% increase for waypoint NSR and over 23% for the action NSR. It shows that RL phase really sharpened the robot's precision.
Which translated to success on these really hard, long horizon tasks. Things like folding a towel, which is a deformable object.
Always tricky.
And this 9-step process called prepare food that involved using a microwave. Lumo 1 just made more progress on average than any of the baselines.
And it showed some incredible real-time robustness. The example I loved was the context-aware arm selection.
Oh, yeah.
The robot's main arm was blocked, so on the fly, it just replanned the whole thing and seamlessly switched to its other arm to finish the job. So it shows real dynamic spatial reasoning.
So a final technical point from the paper was about scaling laws.
Right. They validated what's called the data-constrained scaling law for robotics. And the takeaway is simple. Data diversity is king.
You can't just scale up your model size.
Nope. Policies they trained without basic data augmentations like different lighting or viewpoints, they just fell apart under real-world conditions. You have to scale data diversity.
And just for context, all of this is running on the Astribot S1. It's a bimanual mobile manipulator, very high degrees of freedom, really designed for these kinds of human-like tasks.
So to synthesize this for you, Lumo 1 is this really mature architecture that successfully gets transparent structured reasoning into the VLA control loop. And that's what's driving this huge leap in generalization.
They solved the action modeling problem with that slick spatial tokenizer, and then they sharpened the whole policy with very sophisticated RL.
Right. So the paper proves the value of both the super robust full reasoning mode and the faster partial reasoning mode.
And as these models move into real-time interactive environments where latency is everything, the industry is sort of accepting this trade-off for now. Speed for robustness.
But that leaves us with the big question, right? We're seeing rapid improvements in LLM and VLM latency all the time. Will those improvements eventually just negate this trade-off?
Making that comprehensive, robust, full chain of thought reasoning the default for everything.
Exactly. Will speed improvements just make the entire trade-off obsolete? That's the horizon we really need to be watching.
Right.